Hi everyone. So in this video we discuss two algorithms that are commonly used in current deep learning algorithms or in current training algorithms for deep neural networks. The first is called RMSProp, which is basically stands for root mean square propagation, and the second is ADAM or adaptive moments algorithm. So let's start with the first one, RMSProp. The motivation here is basically to extend ADA-grad or the adaptive gradient algorithm that we discussed in the last video, such that we allow for forgetting past gradients that are no longer relevant. And the reason is that it's typical with the large parameter space that we have in deep neural networks that the cost function will be non-convex, right? And if it's non-convex, then it will look like something like that, right? So if I am in a region right here, right, then the gradients corresponding to a region at the start of training that that is no longer affecting my local neighborhood should not contribute to the step size that I'm having, right? So this was the ADA-grad, the adaptive gradient algorithm, and basically the modification happens in this step here, the R equal R plus G times G, right? And what happens for RMSProp is that we add this discounting factor rho, right, where rho is less than 1, right? So you have rho times R plus 1 minus rho times the square root of the gradient, the multiplication of the partial derivatives element wise, the same as adaptive gradient. And what happens here is that instead of an accumulation of past gradient, we have an exponentially weighted moving average of past gradient, right? And this is the R that we use in the update step, right? So the farther in the past the gradient is, the less its impact would be on the current update step or on the current parameter update, right? So if rho is 0.9, for example, then a gradient 1 step away has an effect of 0.9. A gradient 2 steps away has an effect of 0.9 square, which is 0.81. A gradient 3 steps away has an effect of 0.9 times 0.81, right? And so on. So so this is basically the idea behind the RMSProp algorithm. Now this rho factor is a new hyperparameter that's not in ADA-grad, and again adding a new hyperparameter is advantageous as it adds flexibility, but it can also add a burden of trial and error to figure out the right value, and if you want to make it learnable, then that would add complexity to the learning algorithm, right? But rho controls how fast we forget past gradients, right? So rho basically is affected by how much we believe, like when we encode a value of rho, it's how much we believe that we stay in the same region, how long in terms of training iteration we believe that we stay in the same region, right? Or how long we believe that the past gradients remain relevant, right? So the lower the rho, the more aggressive or the more quickly do we forget past gradients. The higher the value of the rho, the higher that we keep these past gradients affecting the current parameter update, the step size of the current parameter update. ADAM is basically, or the adaptive moment, which is the second algorithm that we discuss in this video, is basically a combination of momentum with the idea of RMSProp, right? And the idea is very simple. Here it's like rethinking of momentum as a first order moment, right? So this is the momentum update, that step right here, right? So you take, so we call it S here. This is the accumulation of gradients, right? And there is a rho 1 factor that tells me how do I forget, that basically controls how do we forget the values of past gradients. And then this part R here is the same as RMSProp, right? So this is the square of the gradient. So we think of the update corresponding to the square of the partial derivatives as the factor that controls the second order moment update to the gradient. Second order because it's the square root of the sum of the squared gradients, right? So it's like trying to predict the expected value of the square of the gradient. That's why it's a second moment update. And S corresponds to updating the gradient itself, so it's a first moment, right? You're trying to predict the expected value of the gradient itself. And then we update, so the delta theta becomes minus epsilon, the learning rate, times S hat, which is the new prediction of the gradient, right? So here, instead of the gradient, I have this S hat divided by square root R hat, right? Which corresponds to square root R. In fact, S hat and R hat are slightly different than S and R because they include what's called bias correction. And the proof for this is in the paper that introduced Adam, but we can discuss a little bit of the intuition behind it. Because the values of S and R are initialized to 0, so there is fear that the first few iterations will be dominated by, or will be biased by this initial value, regardless of the true value of the gradient, right? So because we start at 0, so that's why we include these steps. And basically S hat equals S divided by 1 minus rho 1 to the t, to the index of the time step. And if you think of it as t increases, because rho is less than 1, right? As t increases, rho 1 to the t becomes very small, and this correction step becomes negligible. And the same thing for the correction step for R, right? So this really takes effect only in the first few training iterations, right? So think of the very first iteration, right? So I have S here equal 1 minus rho 1 to the times G plus rho 1 S, right? The old S equals 0 because we initialize to 0. So it's just 1 minus rho 1 times G. And that's why S hat we divide by 1 minus rho 1, because I wanted to get so that we get the actual gradient, right? And in further iterations, the power of rho gets raised because there is a multiplication by rho in every iteration times the old value of S. And the same thing for R, right? So S and R are what's called bias correction step to make up for the 0 initialization of R and S. Okay, now so I have this S hat instead of the gradient, and then we divide by square root R hat. So this is the first moment expectation, which is an RMSProp. It's the exact gradient, and then we divide by the second moment expectation, which is given by R, right? So Adam is really a combination of the momentum algorithm and the root mean square propagation algorithm. And there is a variant of Adam that's called NADM, right? And basically it stands for Nesterov momentum and Adam, right? So instead of the second moment estimate instead of the first moment estimate being governed by the momentum algorithm, it's governed by the Nesterov momentum algorithm, right? So that's a slight variation. And again, these are all heuristics, and they are motivated by modifications to the stochastic gradient descent algorithm. Each of these modifications have a theoretical guarantee by itself, right? So, or have a theoretical justification by itself. So momentum has a theoretical justification. The adaptive learning rate through the division by the square of the root of the square of the partial derivatives. This has a justification. So adaptive gradient has a justification for convex functions. But Adam is a combination of all of these. And NADM is a combination that includes Nesterov momentum. And remember, Nesterov speeds up the convergence of SGD, right? Thank you.